An electric field line emerges from plus Q1 and enters minus Q2. It emerges at an angle alpha and enters at an angle beta. We are interested in finding beta. Now, we know that an electric field line connects two charges of equal magnitude, but here the magnitudes are different. One is Q1 and the other is Q2. We know that the number of field lines emerging or entering is proportional to the charge. So we can say that M is proportional to Q. For an angle 2 beta, the lines entering must emerge as a homogeneous bundle from plus Q1 like a cone of angle twice alpha. Now, the ratio of the number of lines emerging from plus Q1 and entering minus Q2 to the number of lines generated by plus Q1 would be equal to the surface area of the cone by the surface area of the homogeneous sphere centered at plus Q1. So M is equal to N by N, where N is the total number of field lines and small n is the number of lines converged into minus Q2. From here, we can write N to be equal to M times N, multiplying Q both sides, we get M times Qn. Now we can write Q1 N1 equal to M1 Q1 N1 and Q2 N2 equal to M2 Q2 N2. Take this quantity to be equal to S1 and this quantity to be equal to S2, where S1 is the strength of the field lines emerging from plus Q1 and S2 is the strength of the field lines entering minus Q2, which are equal. Therefore, we can write Q1N1 to be equal to Q2N2. And therefore, we can write M1Q1N1 is equal to M2Q2N2. Q1N1 and Q2N2 are the magnitude of the two charges. So we can write M1Q1 equal to M2Q2. So objective is to find the ratio M. A field line emerges from plus Q1 and passes the base of the lower small hemisphere without touching its lower surface. So we have to find the surface area of the cone along with the extension. Let us take the radius of the lower sphere to be mu, then O prime A is also mu. As the angle is alpha, OA is r sine alpha, where r is the radius of the homogeneous sphere centered at plus Q1, where the field lines originate. And we know O prime is at the boundary of the larger sphere. So OO prime is r 1 minus cos alpha. Therefore, triangle AOO prime is a right angle triangle, and using Pythagoras theorem, we can write mu square is equal to r square sine square alpha plus r square 1 minus cos alpha whole square. Solving this, we find mu square to be r square sine square alpha plus r square cos square alpha minus twice r square cos alpha, which gives mu square to be equal to twice r square minus twice r square cos alpha, which gives us twice r square 1 minus cos alpha. Let us take a small area element on the surface of this conical structure and name it delta S. We name its projection delta S prime. Now let's move delta S around the surface area of the conical structure. What we find is that delta S prime has covered the base of the lower hemisphere, which proves that the surface area of the conical structure with the extension is the area of the base of the lower hemisphere of radius mu, which we have already found. We found mu squared to be twice r squared 1 minus cos alpha. So the ratio m is pi mu squared divided by 4 pi r squared. That is twice pi r squared 1 minus cos alpha divided by 4 pi r squared, which gives us 1 minus cos alpha divided by 2. This is the ratio m. Now we derived m1 q1 is equal to m2 q2. So we have m1 to be 1 minus cos alpha divided by 2 times q1, which is equal to m2, which can be written intuitively as 1 minus cos beta divided by 2 times q2. We know that 1 minus cos alpha is equal to twice sine square alpha by 2. Hence we can write sine square alpha by 2 to be equal to 1 minus cos alpha divided by 2. Plugging this value into the above equation, we find q1 sine square alpha by 2 is equal to q2 sine square beta by 2. Further solving, we get sine beta by 2 is equal to sine alpha by 2 root over q1 divided by q2. And this is our answer.